Hello everyone, Dr. Basner here. We're going to do a short lesson on molecular orbital theory. This will be perfect given that you likely may not have had much information in general chemistry about molecular orbital theory, and you can treat this kind of like an intro to molecular orbital theory for someone who's taking organic chemistry, like most of you, for the first time. And so let's start off by talking about molecular orbital theory, but first going back to some of your prevailing bonding theories that we learned about in general chemistry, such as the Vesper theory. So here we have a very simple molecule, CH4. So when we look at both carbon and hydrogen, we could draw an orbital diagram for each of these. Right, so we can ignore the valence electrons in carbon for now. So let's just look at 2s and your 2p orbitals. Let's actually put the orbitals here on the left, whereas hydrogen is only in the 1s orbital. You know, carbon does have that 1s orbital as well, but we're going to only look at the valence electrons. So when we fill in the orbital diagram for carbon, it has 4 valence electrons and hydrogen has 1. So actually what I might be helpful here is let's do hydrogen. We'll keep hydrogen in blue to distinguish the two. So when we think about the molecule of carbon, or the atom of carbon in the molecule of methane, we run into a problem in that these 4 CH bonds are all equal in energy, right? And so if you've taken, since you've probably already taken general chemistry and you know your hybridizations, you will recognize that carbon is something we call sp3 hybridized. And what we do is we imagine that we need a total of 4 hybrid orbitals because we have 4 groups surrounding the carbon. We imagine that these 2s and the 3 2p orbitals hybridize to form new hybrid orbitals that we call sp3. Right, and so we'll use purple to show the hybridization here. So your new orbitals are going to be somewhere in energy between the 2s and 2p. They'll be a little closer to the 2p orbitals because there are a greater contribution from the 2p orbitals. But we have 4 new orbitals, which we call our sp3 orbitals, that are equal in energy. Right? And because they're equal in energy, that kind of agrees with our hybridization theory. Right, so these are your sp3 orbitals. We call them 2 sp3 orbitals if you'd like, because they come from the n equals 2 energy level. And when we spread out the electrons in these orbitals, we can put 1 now in each. And so when you think about the bond that forms between the carbon and hydrogen, one way to think about it is you can imagine that there's each of these 4 hydrogens with this 1s orbital can give it 1 electron to make there for carbon to have a full octet, right? So this blue electron is being shared with the carbon for each of these hydrogens, right? And we have 4 of these, so there's 4 different hydrogens that each have 1 electron in the 1s energy level, and each of these is sharing one of those different electrons from the carbon, right? So that's kind of a traditional way to think about it and how you probably think about it now. And that leads us to molecular orbital theory, where molecular orbital theory is, in a sense, a way to describe what is actually happening in this covalent bond where these electrons are being shared. It's not quite, the truth is it's not quite as simple as just we have the 1s and the sp3 orbital sharing those electrons. You know, the truth is actually much more complicated. And so we can look at some orbitals here before we go into a little more about molecular orbital theory. So we kind of assume that the sp3 orbitals, we actually consider them kind of dumbbell shaped, but a very small portion on one side, right? And then these kind of, your sp3 orbitals fill in the tetrahedral pattern because they space themselves out as far as possible. Right, so those are all your sp3 orbitals, right? If the black arrow is the electron, right? There's an electron in each of those orbitals. And then you have your hydrogens that are in here. The s orbitals are mostly circular, right? But you can imagine they have that electron being shared, right? That obviously looks way bigger than it actually is, but that is being shared, like so, right? And that's the 1s orbital of hydrogen. And these are your sp3 orbitals from carbon. And so, as I just mentioned, sp3 orbitals or molecular orbital theory is an attempt to explain what's actually happening in one of these bonds. And so what we can do is take one of our orbital from each thing that the bond is forming on, form a molecular orbital based on those two things. So if we have a 2 sp3 orbital, right, let's say we're looking at this sp3 orbital right here, then we have the hydrogen 1s orbital. So this is from carbon. And over here we have the hydrogen 1s orbital. That's going to be slightly lower in energy than sp3 orbital, but the s orbitals are always lower in energy. It's probably actually a little bit lower than that, so let's fix this. Probably be about here. The 1s orbital in hydrogen. And so we can describe this bonding between the 1s orbital and the sp3 orbital using molecular orbital theory. And so to do that, if we have our basic energy levels here, we assume that when these two combine to form this new bond, it forms two new orbitals, right? And the energy levels will be a little bit below the lowest, a little bit above the highest. Generally, this is going to be about equal distance if we're just trying to sketch one out, just to kind of place it. And so this orbital right here, these two, the 1s orbital from hydrogen and the sp3 orbital from carbon, combine to form two new orbitals. And these right here are what we call molecular orbitals. So what a molecular orbital is the combination of two orbitals from two different atoms. Essentially, you can think of it like hybridizing to form two new molecular orbitals. And that's the big difference between our VSEPR theories, whereas with VSEPR theory, we're hybridizing orbitals on a single atom, whereas with molecular orbital theory, you're hybridizing two orbitals on two different atoms. And so it's kind of a new way to think about it. And so if we go back to our picture here, there was one electron in the 2s3 orbital. There's one electron in this 1s orbital, and they combine. We still follow our rules for filling electron orbitals, and that we always fill the lowest energy ones first. So there's our two electrons. They form to fill this bottom orbital, and then the top one is left empty. And so what we label these as our molecular orbitals is the one on the bottom we call a sigma orbital. In this case, it's an end-to-end straight line, so this is a sigma orbital. We call this one a bonding orbital. Here at the top, this one that's empty, we call it a not non-bonding, we call this a anti-bonding. And so ideally, if you have one electron from each orbital, they will combine to form one bonding orbital, one non-bonding or anti-bonding orbital, and that's the whole of your new molecular orbitals, right? And so it gets a little more complicated, of course, but we want to start with this particular diagram. This is kind of like your basic, very simple diagram, right? And I also should add that I forgot to draw, so we mentioned our anti-bonding orbital by also having a sigma, and we put a little star by it to indicate that it is the anti-bonding orbital. So this is your basic molecular orbital, right? We're taking one orbital from one thing, one orbital from another. If we take two orbitals and combine them, we get two orbitals out. We get a bonding and then an anti-bonding. So how we would describe that in terms of what do these two orbitals look like? So if this is your carbon, and this is your hydrogen, right? The orbitals look kind of like the orbitals we've been drawing, where your sp3 orbital is kind of dumbbell shaped with more greater side towards the hydrogen, whereas the hydrogen is just an s orbital that looks kind of like that. And then the bonding itself, we just kind of picture there's an overlap between the two orbitals. And then this right here is our sigma bonding orbital. The anti-bonding orbital, which is a little higher in energy, so we'll draw it up here by the anti-bonding orbital, is kind of the opposite, right? So the electrons will take place, if there was any, but we can kind of see here, this is empty. It would go or be placed in an orbital that's away from the direct line between the two atoms. Same thing with the 1s orbital. It would be placed away from right, the indirect line between the two atoms. So the right, and so that's how this works, right? If we have electrons here in our anti-bonding orbital, they are not contributing to the bond. In fact, they're actively making it so that bond can't form. And so, right, and then also keep in mind, I know there's probably maybe some people out here are gonna comment. This is just a very simple look at it, right? We're kind of describing this as for people who have never really gotten into molecular orbital theory before. So keep that in mind. Okay, so let's kind of move on here to a little more complicated aspects of molecular orbital theory. But we can describe any bond like this. So let's do another single bond here. So let's make our organic molecule slightly bigger. Right, so now we'll use ethane. All right, let's say we want to use molecular orbital theory to describe that carbon-carbon bond. Right, so both of our carbons are sp3 hybridized. Right, and so an sp3 orbital from carbon 1. And over here on carbon 2, we can have an sp3 orbital in the middle. Right, these two will be roughly the same in energy because, you know, they're pretty much in the same identical environment. And so these will form a molecular orbital down below and one up above. So these two hybridized form your sigma bonding orbital and then your sigma anti-bonding. Right, we have one electron here in each that combine to fill up the bonding orbital. Because we have two electrons in the bonding orbital, we have a successful bond. And so that's kind of another interesting tip. If you take the number of electrons in bonding orbitals, then you subtract the number of electrons in anti-bonding orbitals and divide that by 2, you actually end up with the bond order for that particular molecule, or for that particular bond, right? So in this case, we have 2 electrons in bonding orbitals, 0 in anti-bonding. If we divide that by 2, we get a bond order of 1, right? And the bond order of 1 is essentially a single bond. A bond order of 2 is a double bond. A bond order of 3 is a triple bond. So, right, this kind of agrees with how we drew our Lewis structure here. We have just a single bond between the 2 carbons, no spare electrons or anything to worry about in anti-bonding orbitals. So overall, you know, we don't want to complicate it too much, right? We're just taking one orbital from carbon 2, one orbital from carbon 1. You make a bonding and anti-bonding orbital out of it. So let's move on to something slightly more complicated. Let's look at an alkene. So we'll just do a very simple alkene. Let's draw the carbon in. So let's say I want to model that orbital. I want a molecular orbital of the carbon-carbon double bond, and I want molecular orbital for this carbon-hydrogen bond. We'll use blue to describe the carbon-hydrogen bond, and we'll just use purple for our alkene. So this time we have a little different situation because our carbon here is sp2 hybridized. They're both sp2 hybridized. So before we start our molecular orbital, let's just kind of look at the orbital diagram for just the carbon, right? So here's our base carbon, right? 1, 2, 3, 4. Let's do this one going up. So when we hybridize these molecules, we're only going to hybridize the S and 2 of the P's. We have, these are your sp2 orbitals, and we have the p orbital that's unhybridized left over. Right? So we have one unhybridized p orbital that just stays a p orbital. And we'll put one electron here. And so if we think about our structure here, the carbon-hydrogen bond is bound with one of the sp2 orbitals. So if we start with the carbon-hydrogen bond, on the carbon, we'll do in blue. For carbon, we're taking one of these sp2 orbitals, which has one electron in it. We're going to combine that with the 1s orbital of hydrogen, because that's what orbital is making the bond. Hydrogen, we have our 1s orbital. Like before, we have one that goes lower in energy, one that goes higher in energy. Roughly the same distance from the 1s to the bottom, s to the sp2 to the top. It'll be roughly the same distance there, and then we have those right there. All right, so the 1s orbital of hydrogen and the sp2 orbital of carbon combine to make your sigma bonding orbital and your sigma anti-bonding orbital. There's only 2 total of electrons, so those fill up the bonding orbital, which allows us to have a successful single bond. Right, and that's what we see in our structure, a single bond between carbon and hydrogen. So let's now look at the other molecule here, the carbon-hydrogen double bond. This time we are doing things a little differently in that we have over on the carbon side, we have a sp2 orbital, then we also have the p orbital making a molecular bond. So we get the p orbital from each one will combine, right? Because the double bond is made from pi bonds, so we're going to have those make a bond here, carbon 2, carbon 1. And actually, now that I say that, we should go back and look at an orbital diagram, or just look at the orbitals involved in bonding. Right, so here's the 2 carbons. You have your sp3 orbitals right here, or sorry, sp2 orbitals, not sp3. It's very similar to an sp3, but right. So those, you have the sigma bond, and then you have your empty p orbitals. Empty p orbitals are not, sorry, they're not actually empty. Those are making the pi bond, which is above and below the straight line between the 2 atoms. Those are your sigma and pi bonds. And so we can represent that right there in a molecular orbital. Right, first we'll make a molecular orbital because the 2 sp orbitals will make a single bond. Right, so we can do that pretty easily. Right, so the sp2 orbitals hybridize to make a molecular orbital. Right, if there is 1 electron in each from as we saw from our orbital diagram, we fill up our sigma bonding orbital, which makes sense. So we have, right, so this right here is the sigma bond, that how we represent our sigma bond. We have no electrons in our antibonding orbital. The p orbitals will hybridize the same way. Let me make this a little taller so it's not as cramped. It's up a tad. Okay, so those will combine to make a bonding orbital and an anti-bonding orbital, just like sigma. The big difference though is this one's actually our pi orbital. This is our pi, we call that pi anti-bonding. So we get one electron from each combine to go to the pi bonding orbital. And the pi anti-bonding orbital is empty. And so we can describe these orbitals if we were just talking about these orbitals in particular, if we wanted to draw a picture of them. The sigma bonding orbital, again, is going to be looking kind of like this. So sigma bonding. Your sigma anti-bonding would be more like this, assuming that the other carbon's right there. And then the pi orbital, these are the two carbons. The pi orbital is kind of leaning in, right? As if it's helping make the bond, right? They'll be towards each other, whereas the pi anti-bonding orbital is kind of the opposite. So your pi bond is going away from each other. So, your anti-bonding orbital, if electrons were here, they would be actively working against the formation of a bond. Whereas with the bonding orbitals, they're actively working towards making a bond. And so if we kind of do the same bond order thing, this time we have 4 electrons in bonding orbitals. We have 0 in anti-bonding divided by 2. So we get a bond order of 2. And that makes sense given that we already kind of know this is a double bond. But we now have molecular orbital theory where we can sort of confirm that we are in fact seeing a double bond. And so this is very similar to how we look at molecular orbital theory, or at least the start of molecular orbital theory from an organic perspective. We're going to get into a little more complicated stuff, or you will, in the second semester of organic, is when we look at more complicated things like molecular orbitals of aromatic compounds. Right, and so this right here is benzene. It's a very common organic molecule. And so each of these right here are sp2 hybridized. So if you didn't draw in the double bonds, right, you'd have a pi orbital there, here, one here, and one there. Right? And so it turns out that there's 6 electrons. 6 electrons in pi bonds. And then they just kind of rotate around these 6 pi electrons. In fact, what we do is we describe those using molecular orbitals once we get to the more advanced things. And so the molecular orbital for benzene looks kind of like this. And it's basically you take these, right, there's 6 p orbitals, and those hybridize to molecular orbitals in energy somewhat similar to this. Small molecular. So if we have 6 electrons in these pi bonds, right, we have 1, 2, 3, 4, 5, 6. So these right here are your bonding. These are your anti-bonding. So from a bond order perspective, there's 6 minus 0 over 2. So we got a bond order of 3, which kind of makes sense because we have, if we're only looking at the pi bonds, we have 1 pi bond, 2 pi bond, 3 pi bond. So that's where that bond order of 3 comes in. But we're looking at a whole series of 6 atoms, so bond order isn't really the best option. We don't really need to do bond order in this case. And so that's how we start looking at aromatic compounds. We can do similar things, say with a cyclopentene type molecule. Again, you're going to be doing more of this later on, so this is more advanced molecular orbital stuff. So the molecular orbital of cyclopentene diene, or cyclopentane ion, looks kind of like this. And so there's resonance around here where, right, you can just rotate that around several times. We still have 6 electrons. Those are all your bonding electrons. And so You can use these molecular orbitals to describe these neat multi-atom aromatic compounds. But for now, right, we're just looking at it to describe very simple bonds. And so all you really need to do is take, let's actually move back here, take the orbital from that's making one of the bonds, take the orbital that's making one of the other, combine those to make a bonding and anti-bonding, and then fill in the correct number of electrons. And so let's do one more example here. So let's do, say, a ketone. A ketone might be a good one to do. So you have right here an sp2 carbon, right? Right, you can think of this kind of like an sp2 oxygen, 2 lone pairs, and then the rest, we'll just kind of look at this particular double bond. So if you have the carbon, which has an sp2 orbital, then it's a pi bond, so we also have a p orbital. So you can imagine a p orbital from the oxygen and an sp2 orbital. Right, and so you combine these, right, we'll make our bonding orbital, antibonding, bonding, antibonding. So this is our pi bonding, pi antibonding, sigma, and sigma antibonding. So we have 1 electron in each, right? Those fill up the sigma, this fills up the pi, right? And so there's where you get your 2 particular bonds. One more example here. So let's look at a carbon-carbon triple bond. So we'll just do a very simple carbon-carbon triple bond. Right, so now we're dealing with carbon that's sp hybridized instead of sp2 or instead of sp3. But we have 2 pi bonds. So from a orbital perspective, right, you have carbon, which has its sp orbitals. So this is sp. Right, you're going to have a sigma bond, right, between the 2 sp orbitals. Then over with the hydrogens, right, those have your 1s. You're going to make a sigma bond between the sp and the 1s. You're going to have the 1s, so you have 3 sigma bonds here. And if we just look at the pi bonds, right, we have one kind of on the y Cartesian coordinate, and you have one on the z coordinate. So you have purple can be the z coordinate, so you have pi bond 1, and blue can be the y-axis, so then you have the pi bond between those other 2 p orbitals. So you have you have 2 pi bonds 90 degrees apart. All right, and then this really prevents rotation because you have 2 pi bonds kind of locking it in place. So to describe this from a molecular orbital perspective, what we want to do is we're going to take 2 p orbitals from carbon 1. So that's p, we'll call this py and pz. Then we have an sp orbital, it's a little lower in energy, 1 electron here in each. The carbon 2 over here is sp, and then you have the py and pz. So these 2 pi orbitals will combine to make 2 pi bonding orbitals. Then we have 2 pi anti-bonding. And over here, again, I kind of cramped this a little, so let's make some more room. Wrong tool. And so the 1 sp from each carbon will combine to make a. Let's move these a little closer together so we're equal distance apart. So we're going to make a sigma bonding, a sigma anti-bonding. Arrows in, or you cannot put them in, doesn't matter. And so we get 2 electrons here. And down here we got 4 electrons in the pi orbitals. So those fill up like so. So now we have a total of 6 electrons in bonding orbitals. We have no electrons in anti-bonding orbitals. And divide that by 2. So we get a bond order of 3. which makes sense because we had a triple bond. So that's how we might describe the molecular orbitals for a triple bond. So that's kind of the basics you need to know about molecular orbital theories to really get started. This will take you, for the most part, through all of what you need for organic 1. For organic 2, again, we're going to be looking at multi-atom molecular orbitals, which really this is about all that really is. Where you combine several p orbitals from several different atoms in aromatic compounds, because that aromatic makes all these electrons are kind of hyper shared, so it kind of makes unique orbitals out of it. But for very simple stuff, for organic 1, you're going to be dealing with very simple anti-bonding orbitals. You might notice that we have yet to put an electron in an anti-bonding orbital, and that's because we're dealing with very, very simple molecules so far in organic chemistry. There's nothing that we have got to yet this semester or even next semester where we're going to fill in the anti-bonding orbital. So, right, so basically we're just going to combine orbitals from 2 different atoms to make a bonding and anti-bonding, whether it's pi or sigma. It just kind of depends on if it's single, double, triple bond. Right, and if the more bonds there are, the more we just incorporate pi orbitals instead of sigma. That's where we're going to stop today. So let me know if you got questions. I'll be happy to answer those. And I will see you all next time.